Awesome, welcome. So we're Rachel and Holden, and we're going to talk about Spark auto-tuning, or magical spells to stop your pager from going off 2 a.m. No guarantees. So my name is Rachel Warren. My pronouns are she and her. I'm a data scientist, where data scientist means software engineer that works with data at Salesforce Einstein. I used to work at a company called Alpine Data with Holden. I've basically spent all of my short career, I'm not very old, building pipelines with Spark. And I'm also the co-author with Holden of High Performance Spark.
And yeah, I'm Holden. My preferred pronouns are also she or her. And I'm a developer advocate at Google. I'm also on the Apache Spark PMC, which means that it is really hard to get rid of me. It's like tenure, except I don't get paid, so that kind of sucks. But it's pretty cool because Google pays me. And I've worked at a bunch of other companies, including Alpine, where we work together. One of the things which I've started doing recently, which I'm trying to get people more interested in, is open source code reviews live streamed. And so if you're interested in seeing how the Spark project and other big data projects do their code reviews, you can follow me on Twitch and YouTube. But also definitely buy our book, several copies, of course. In addition to who I am professionally, I'm trans, queer, Canadian. I live in America on a work visa that they're debating whether or not they want to keep, which is a lot of fun and part of the leather community. And this is not particularly related to Spark tuning. There is no secret Canadian garbage collector that we have that save us from all of this pain. But I think it's useful to remember that we all come from different backgrounds. And if we work together, we can build really awesome stuff. Or if we spend all of our time fighting with each other, we're just going to burn the world down with shitty models and bad data. So be nice to each other and don't fuck up. OK.
So I don't have very much data about you, but I'm going to assume that you're nice people, but I don't know that. I do know that you like pictures of cats, and you're probably interested in using Spark, or maybe do use it in production because you showed up to this talk at 5:30 in the evening. And I'm also pretty sure that if you showed up to this talk, you're tired of spending so much time fussing around with Spark settings. So the goal of this talk is to give you the resources to programmatically tune your Spark jobs so that you can run them both consistently and efficiency. And we'll talk about both time and money. So we're going to start with a rundown of kind of the most important Spark settings and what they mean in the context of the Spark execution environment. For those of you who've been using Spark for a long time, this will be a little bit of review, but it should lay some groundwork. And then we're going to give some examples of errors and performance problems that we can see while running a Spark job and how changing settings can address that. And then I'm going to talk about tuning jobs statically, so without historical data, but programmatically. And then we're going to show this kind of proof of concept open source project that Holden and I have developed that will collect historical data about your Spark job and then do some auto-tuning based on that. And then lastly, we're going to give kind of a rundown of other auto-tuning Spark tools that are out there today. So this is a big data talk, and that means that I have a word count. So this is a word count application. We start by creating our Spark conf. This is where we would put all of the settings if we were to add some. We start up a Spark context. Starting that Spark context corresponds to starting that Spark application. However, no code is executed here until the end of this block when we save as a text file. We call that an action, and that triggers this Spark job. And the Spark job is going to be composed of 2 stages. The first stage is everything that happens before the data movement step, triggered by this reduce by key. And the second stage is that saving as output file. So these are sort of the Spark settings that if you're running in a distributed environment, you really must set. So the executor memory is the size of the Spark worker, the driver, the size of the driver node. Executor vcores is the number of CPU cores to put to each executor. And then we either have to tell Spark how many executors we want to use, or we can enable dynamic allocation, which is Spark's way of doing that for you. So what do these mean? So this sort of hokey diagram is meant to give you some picture of what a Spark application looks like while it's running. So the empty blue circles are the nodes on a distributed system. So on one of these nodes, if we're running in cluster mode, we have some Spark driver. The driver memory is basically the size of this pink box. And then each of the executors are spawned up on some of those nodes. So a couple things to point out. The executors associated with one application have to all be the same size, and they have the same number of cores associated with them. We can put several executors on one node, but one executor can't span multiple nodes. And to get some terminology straight, a task is basically Spark's labor using one core to compute one partition, which is the piece of your distributed RDD. So a couple of heuristics for these settings. Driver memory, in my experience, is unlikely to improve that efficiency metric, but it can be required. You might need to increase it to prevent your job from failing. And just a couple of notes about executor memory. It can be kind of a binning problem. So we want to be thinking about not only like how big can the executor possibly be, but how can I set it in such a way that I can put an optimal number on my cluster. We often have a trade-off between setting a few really big executors or more smaller ones. And I think the biggest pros of a bigger executor is you're less likely to run out of memory, but if you're running with dynamic allocation, it can be harder to free up enough space to place those large executors on your cluster. And so again, one core corresponds to one task, so the total number of concurrent tasks is equal to the total number of cores times the number of executors. And one thing I found to be really important when writing systems to dynamically configure Spark jobs is we want to think about burning through our memory and CPU resources kind of equally. So if you write an application that's taking 80% of the CPU but only 20% of the memory on a shared cluster, you're basically going to make it so that there's memory left over, but nobody can use that memory because there's no CPU left. So dynamic allocation is really powerful. It's basically the only easy way using Spark to change the number of resources that a Spark job has during the course of an application. So the way that it works is we set an initial number of executors, a max and a min, and then Spark will add executors while there's a backlog of tasks. And the amount of time the tasks have to be waiting is configurable. And then it will decommission executors between jobs once they've been idle for some amount of time. And dynamic allocation is really most important when you're in a cost-sensitive or a shared environment. So if you have your own giant Spark palace where you're running these things, you can just use the whole cluster all the time, and this probably doesn't matter so much. But if you live in the real world, dynamic allocation is a way to kind of control, make sure that you're using only the resources you really need over the course of a long-running Spark application. And it's also most important when we have big, complicated Spark applications. So machine learning is a really good example of this. So if it's something that's running maybe hundreds of Spark jobs in one application as it's doing iterations, we might want to give those jobs a different amount of resources. And dynamic allocation is kind of your one way to do that. All right, so let's say you've come up with the number of cores, the executor size, you've configured dynamic allocation, and now you're running your job. Holden's going to talk about a few things that could happen.
So since this is Spark, the first thing that we're going to do is have an out-of-memory exception. Yay! And for the people not laughing, you're either really lucky or just don't like my sense of humor, which is fine. So there's a lot of different ways we can get an out-of-memory exception in Spark. Do you want to raise your hands if you've had application memory overhead exceeded? Shit, that's a lot. OK. How many people have had just the regular Java OOM on their workers? That is way less than I expected.
How many people are using Python?
Oh, yeah, OK. How many people are using PySpark? OK, cool. So I guess this gives us a... Should have picked a different first example. But we're going to assume that you've run out of Java heap space. But we can get different failures, and we can solve them in similar ways. Well, Right. So one of the things that we can do is just throw more memory at the problem. This is great. I work for a cloud provider. If you are on our cloud, I heartily endorse just giving me more money to solve your problems. That is a definitely scalable solution until your credit card is declined. However, if your credit card is nearing the point of being declined, or you don't buy your memory from me, there are other possible solutions we can try. One of them is we can try increasing the number of partitions. And the idea is that with some amount of flexibility, we can think of the partition as like a unit of work that gets assigned. And if we run out of memory while we're working on a unit of work, if we make our units of work smaller, we might not run out of memory as often. We can do this sort of by changing the default parallelism. Unfortunately, for a lot of things, this doesn't actually affect what you would think it does. Your partitioning actually depends on other factors, and so you can explicitly pass this in code rather than changing settings, and you can do this repartitioning. There's also a lot of things we can do with our code, right? We've both written a lot of really terrible code, and our book has a chapter on essentially bad ideas we came up with, and why those data structures were not great. So that's, for the most part, not things we can fix super easily with tuning. Lower cluster utilization, idle executors. This is a sort of different problem which we can solve with the same knob. And so essentially, one of the things which we can sometimes get is our task is mostly finished, but then we have a few computers or a few executors doing some work before our task is finally finished. How many people have that experience? Okay, that's a lot of people again. So okay, at least we got some of this content right. And so there's, to some degree, we can solve this by increasing the number of partitions. And this can be because either we're in a case where we do like all of the work, but then we've got like 4 remaining partitions, and so now our cluster just needs to go and do those 4 remaining partitions. This can also come from just if our data is unevenly distributed. And to some degree, we can fix that by increasing more partitions. However, if our data is really, really badly distributed and like individual keys are super hot, adding more partitions will just make our job slower. So that's cool. You can try turning this knob and see if it gets any better. And if it doesn't, then oh well. Then you just have to change your code. And so that sort of can help us some of the time. Shuffle spill to disk is another thing which can be bad. It is not the end of the world, though. And we should think of shuffle spill to disk as Spark saving us from an out-of-memory exception. And given the number of out-of-memory exceptions we get, that's really useful. And so this comes from Spark sees that it's about to run out of memory, and what it does is it writes all of the work that it's done up until now out to disk, and then this allows the garbage collector in Python or Java to free up some memory. And this is really useful. On the other hand, disks are a lot slower than memory. So spilling to disk is like not super happy, especially if you are working with magnetic disks. It's very sad. Also, Google sells SSDs. But, you know, so yeah, once again, problem you can solve by giving me money, or problem you can solve by changing some different knobs. One of the things you can do is you can have larger executors or smaller partitions, so you don't have to spill to disk as frequently. Another option is you can change your buffer size, and you can change the number of threads in your shuffle service, and other parameters like block size that are used in your shuffle service, which can give you more efficient utilization of the resources you do have. And those are numbers that you can just try tuning by hand and keep track of in a Google spreadsheet, Salesforce, what's it called?
A Salesforce instance.
Salesforce instance, or Excel spreadsheet, and manually keep track of by hand. Or you could use a computer to make a table and then figure out the best setting for your machines, and then just keep it and never update it, because that'll definitely work. Sarcasm. Okay, or not. Very well. So that's okay. We can solve some of our previous problems some of the time by increasing partitions, but is there any downside to just setting that to a really, really big number and walking away? And the answer is yes. On our driver program, we have to keep track of information about all of the partitions, and this has some overhead. But more importantly, each of those partitions results in a task which has to get scheduled, and scheduling tasks is not free. Scheduling tasks is not as expensive as it used to be, but this can be especially painful for Python users. And so if you have really large numbers of partitions, you can end up having long spin-up time. The other sign is if you have a long file write time to the relative amount of I/O you've got. This can be a sign that you're writing out a large number of small files to a block store that doesn't really like small files. It likes big files. And so this can be a sort of related sign. Yep. OK, cool. So I'm going to, for the 8 Python users in the house, there are some really fun settings that we can do with Python. And application memory overhead also impacts people who use off-heap storage and all kinds of other things as well, besides just Python. I honestly thought there were more Python people here, so that's why I was focused there. And essentially, Spark just says, I want most of my memory for Java, and I'll save 10% of it for everything else. And that's not the worst heuristic in the world, but it's not perfect, so we gave you a knob, so then when it doesn't work, it's your fault rather than my fault. And that worked up until a point, and we sold a lot of support contracts back when I worked at a different firm. But now you need to set this knob. To some degree, we can automatically set this based on the properties of our job. We just don't. So we can use tools to do this for us. So if we use off-heap storage, we need to increase the amount of application memory overhead. If we're using machine learning, which is talking to off-heap things, then we also need to increase the amount of storage. If we're using Python or R, then we really need to increase the amount of off-heap storage. And to some degree, Spark on Kubernetes people are actually trying to solve this problem. In their latest PR, it's really exciting because then we can eventually get rid of this slide in 5 years. And so that'll be cool. Buffers and batch sizes. Arrow is really awesome. It can make Spark a lot faster if you turn it on for Python users. The only downside is we didn't know what to set the batch size to, so we picked a number and made it a configuration parameter rather than actually figuring out what the right batch size was. So now you all get to figure out what the right batch size is and share that information with each other. And so this is a thing that we can tune. If you have highly variable sized data, tune it more conservatively. If you have more consistently sized row sizes, you can tune it very aggressively. We also have this really cool property for when we want to start spilling to disk in Python. And the really cool thing is the default value of it is higher than the amount of default memory we save for Python. So you'll normally get an out-of-memory exception before we spill to disk. Yay! Oops. Anyways, so just change this number based on the amount of memory that's being left aside for Python and set it a little more conservatively than we did by default. And so that's cool. So tuning can help us with a whole bunch of things we've seen, right? Low cluster utilization, it can help us save money. Out-of-memory errors, apparently everyone gets those, and probably no one likes debugging them, unless your contractor is paid by the hour, in which case that's fine, no judgment. And reliable deployments. But I want to focus. Reliable deployments only happen if we continuously tune our application, right? Because what will happen over time is our clusters will change, the data input sizes will change, all of these things will change, and if we just keep the same configuration parameters from last year, our job is going to behave really poorly, and it'll eventually get to the point where it starts paging me at 2 o'clock in the morning, and that's really probably not what you want to do in your life, right? Occasionally updating the tuning, even if it's by hand, is better than getting woken up to a failing pipeline. I don't know what your SLAs are, but I have nightmares from when I worked at Amazon with data pipelines, and that Motorola pager. Oh, God. OK, anyways, but that's OK. Don't worry. Our jobs can still fail. So even if we do this right, we can still bill our clients for that 2 a.m. call out around Christmas time when money is getting a little tight, and we're like, it'd be really nice if the cluster had a little hiccup. I'm just saying. I mean, more realistically, it can still fail for lots of reasons. Unbalanced shuffles, silly shuffles, serialization exceptions, you can tune away actually some of the time. Please never do that. Just debug your serialization exception. Don't just try changing serializers until it works. That is not a good solution. That is a great way to have an unmaintainable mess. And Python, OK, so Rachel wrote this slide, and I love Python, but it's true, we can't really tune away the fact that we're using Python. There will always be some overhead from it. we can do things to make it better, but at the end of the day, when we start going outside of the JVM and Spark, there's always going to be some overhead, even if we're amazing. So that's enough like sadness about ways our software can fail. Let's watch it fail. Oh wait, this went from sadness to sadness.
Well, we're gonna watch the software that we write fail, rather than the software written by the Spark committers.
Okay.
So we've kind of described this Spark tuning process as you look at your cluster, you use some heuristics, you make a decision, you run it, you watch it, it fails, you change it, you run it, you watch it, it fails, you change it, and that's all well and good until you work for a really big company that's submitting billions of Spark jobs in production. And then we're going to need a different way of doing this. So I'm going to argue that all of this Spark tuning really boils down to 4 factors. So there's the execution environment. The question is really, where is this job going to run, and what are the resources it has available to it? The size of the input data. So very often we have a data pipeline that's running the same logic in the same environment, but on different input data. So we want to know something about the input data and adjust according to that. The kind of computation. So a Python job needs different settings and tuning than, say, a Scala ML job. And then, really importantly, the historical runs of that application. And I actually think we can get almost all this information programmatically. So the execution environment's quite easy to get programmatically. I have a link there to a blog post that I actually wrote that basically runs down the Yarn API call for everything you would need to know to configure a Spark application on Yarn. So basically, if you're in a location where you can submit a Spark job, you're in a location where you know enough information about your cluster to know how busy it is, what resources you have available, how big each node is, et cetera. Input data is actually, I think, a little bit more complicated than it can seem on the surface. So obviously, the size of the input data on disk is really easy to determine before you submit a Spark job. But Spark jobs can have multiple stages. So understanding how big the size of the input is going to be for each stage is a little bit hard to do without historical runs. And we also care a little bit more about what the data is going to look like once it's read into memory, and something about the shape of it. So as we've mentioned, the distribution of keys in a shuffle is hugely important, perhaps more important to shuffle performance than the raw number of records. So to guess this, there's a number of things we can do. We can look at, if we have schema information, we can use that and kind of piece together a heuristic of how much is the data going to expand once it's read into memory. We can look at historical runs. We can look at the number of part files. Sometimes that can tell us something about the keys. So this formula is actually taken from a really great Sandy Risa blog post that suggests the following heuristic for setting partition size. So if we think of a partition as kind of like the slice of our data that each task is processing, we want to make each of those slices small enough so that each of the cores can process a full slice in memory on the executor. So you'd have something like the size of the input data in memory divided by the amount of memory available per task on the executors. So this would be an example of a function that computes the available task memory on each executor. And then you could, if you had a heuristic for input data size, you could set the partitions based on this. So this would be a static configuration. But again, this is not really any great substitute for having some information about how the job really did with these settings. So if we could have anything in the world, I think we'd probably want something like the following kinds of historical data. We'd want some information about our cluster. Are there nodes that are down? Not just how busy is it right now, but if we're running at a particular time in the day, how busy might it be in the future? We would definitely want everything that's available to us in the web UI. So how big is the stage? How much did it read? How long was serialization cost? What kind of computation was run? Was it Python? Was it streaming? Who ran the computation could be important if you're working in a shared environment where you have lots of different users. And most of this is actually possible to get programmatically. So for a human, there's something called the Spark History Server. If you if you work in a dynamic environment, I would really recommend talking to your sysadmin about setting this up. It lets you save all that web UI information so you can see it after your job has died, along with the logs. And we can do something kind of similar with the program. So Spark exposes this listener interface, and what we can do is start a listener in our application code and then save the things that that listener observed to some persistent location, and then read that in before we launch our job. So Holden and I have built this kind of proof of concept application that does exactly this. So this is built on top of an existing project called Spark Measure, which basically exposes Spark listeners to capture the information that goes into the web UI. So what we've done is create a directory scheme with Spark Measure so that when you start an application, it will save successive stage metrics about each run of that application in such a way that we can read them all and get kind of a list of like, this was how it did in each stage with these configurations. And so we can then read that in, run an optimization function, and then adjust the settings that we're using. So I'm going to run through some code pretty quickly, but this is all, it's all up on GitHub, so you can check it out in full detail. I've also edited it down so it's a little bit more concise than it would need to be in practice. So Spark Measure exposes this flight recorder, which automatically saves metrics. So we're going to start that up. We're going to start a new listener and add that to our application code. So that would look like this. And then once we've saved the metrics, we can read them in a subsequent run of the application by going and fetching them from the directory. And so to use this, we would go through this process of getting the metrics we've already done, running our optimization function, and then creating a new Spark conf, and then starting up the Spark context. So this all has to happen before we start the Spark context. So to illustrate this, we talked a lot about partitions in this talk, so I'm going to show a little function written in this project that would try and auto-tune the number of partitions. So I'm assuming that setting partitions roughly follows this pattern where it's like increasing that number makes your job get better and better until some point where it gets worse or fails. This graph is based on no numbers, to clarify. So I'm trying to code up something equivalent to keep increasing the number of partitions until what we care about stops. Something really important to note is that the Spark default parallelism parameter is the one that I'm tuning. That's the default that's used for all stages if it hasn't been set in the code. And partitions is a stage level parameter. So ideally, you would actually want to tune each stage in a job with a different number of partitions. But what I'm doing is because I'm setting the default number, I'm just looking at what is kind of the most expensive shuffle phase and then tuning just that stage. So for the purposes of this talk, I'm considering the most expensive shuffle stage just to be the one where we have the biggest shuffle right. But there are a lot of different metrics you could argue you should use there. And what defines better? I think this is really the money question in optimization problems. So there's often this trade-off between speed and efficiency. So is our goal just to run this as fast as possible, or is it to make sure the cluster is as fully utilized as possible? One interesting metric we could use for fully utilized, which is probably a little bit noisy on a shared cluster, but we could do some calculation of like how long did it take versus did the whole stage take versus how long did each of the tasks take. So theoretically, if each task is distributed perfectly on the executors, this equation should be relatively equal. We could also just look at like what makes the stage faster. So in my example, I've chosen to use executor CPU time, which is the total CPU time across all the tasks. But we could really look at anything that Spark measures. So this function is taking a list of that most expensive stage info for a bunch of runs of the same application on the same input data and doing an optimization based on that. So this first case is this initial set of the partitions. So assuming we have no historical data, and we don't have a good heuristic for the size of the input data, one thing we could do is just set the number of partitions to the total number of concurrent tasks. So that's, again, the number of executors times the number of cores. If we have one run, then we can tell pretty specifically how big the input data is. Here I'm calling out to this function I showed before that's determining the number of partitions based on the memory and the executors and the input data size. And then in this best case where we have a number of previous runs where we use different partitions, we could just look at those runs and see, does it look like increasing the number of partitions is helping this application improve? And if it doesn't look that way, we can use whatever's worked best. And if it does seem like increasing the partitions will help, we can keep increasing them. So I would totally recommend coming up with a solution similar to this. There are a couple of requirements. It's assuming that you are creating the Spark context. So if you're running in a notebook and the Spark context is already created for you, it's going to be hard to do something like this. And it also requires you to know enough about your system to have a persistent location where you can write these metrics and then read them in again. But those are kind of the only big requirements. And this is, again, it's really a proof of concept, and I want to point out just how much more you could do in this paradigm. So with all the information we've already saved, we could look at setting tons more settings. So I don't do anything with executor memory, but you could do a lot. So you could look at the cluster versus the historical runs of the job and adjust that. We could surface warnings about data skew and key distribution. A big limitation of what I built so far is that we don't actually get any information if a stage fails. But there are ways that we could do that. So there are other Spark listeners that keep track of failures and task failures. And so we could read those in and compare that with previous stage duration and come up with something smart to do once we see the job fail. So that could be additional information as well. All right, that was a lot of code. So I'm going to take a nap, and Holden's going to tell you about other code that does this.
Cool. So there are a lot of other tools as well. And as we pointed out a few times, sometimes the right answer is not tuning. Sometimes the right answer is refactoring our code to do something smarter. And there's actually some really cool tools to help us know when the answer is changing our own code versus trying to fix it with tuning. One of them is SparkLens, which is kind of neat. And it has a whole bunch of different analyzers, and it can tell us things like if our data is too skewed, or if other things are going wrong, which we might want to fix either with tuning or with just changing our logic. And just changing our logic, I want to be clear, is a lot of work. So I probably shouldn't have said just, but bad habits. Dr. Elephant is also pretty neat. It has a whole bunch of configuration heuristics, which is like, and it applies these to a whole bunch of different settings. Some of them I wouldn't necessarily give to a computer to auto-tune, like the serializer, but that's just a personal preference, and they clearly have a different preference, because changing the serializer normally causes my code to fail, and I would rather that be my fault than the computer's fault, because then at least I know what happened. In addition to this, you probably need better monitoring than you already have in place. How many people feel confident in their Spark monitoring? That was no hands, which either means everyone is really tired and looking forward to like the happy hour, or no one trusts their monitoring. And so there's a whole bunch of different tools you can do to monitor Spark, and especially if you're going to have a computer program in there randomly changing settings for you, hopefully not randomly, but if you're going to use some high quality software that was made over beers, you probably want to know if things are going to catch on fire, because it's better than finding out at 2 o'clock in the morning. Also, if you want to come chill on a beach, I'll be in Spain on Friday. And in San Francisco, I'll be talking about accelerating TensorFlow and Python. And Scala Days, New York, I forgot to write down what I'm talking about, but I'm sure it's great. And I'll be in Berlin, Amsterdam, Portland, and New York. And then one day I'll go back home. That'll be lovely. I'll see my own bed. Oh, I almost forgot our most important slide. This is our book. You should buy it. How many people have a corporate expense account? Come on.
They really
Okay.
are asleep.
Everyone, no. People are just, they know where this is going. It's about as transparent as, well, I don't know, used car salesperson. So for those of you who raised your hands or were laughing, please buy several copies of this book. You can help a developer from turning to a life of enterprise support contracts. One copy of High Performance Spark buys us each about 1/4 of a cup of coffee. And if you buy the ebook version, that could be almost 1/2 of a cup of coffee. And it's a lot harder to return the ebook version. So please buy several copies. Not with your money. Okay, cool. So that's pretty much it. We've got like 3 minutes. So if anyone has questions, just come up and talk to us. Otherwise, we'll see you in the expo hall.
Yeah,
Awesome.
We'll be around for happy hour.
Cool. Thank you all.